This is the linear algebra equation, lecture number 7. This equation is deceptively complicated. It looks simple, right? Y is equal to x, or b is equal to ax, depending on what we put here. It seems like about as simple an algebra problem as we could think of, and yet it is deceptively complicated. So here we're talking about linear algebra within this unit. So the basic linear algebra equation says this: given the equation ax is equal to b for some matrices a and b, can we find an x that solves this equation? And if not, how close can we get? How close? So this is a little bit different when we talk about close. That's why we have it in parentheses. Now this lecture is probably one of the longest lectures in the entire semester, so bear with me as we plow through a lot of material. So we first define the matrix inverse. So in our last lecture we talked about addition, subtraction, and multiplication of matrices. Didn't talk about division. So in this lecture we're going to talk about division of matrices. Actually, there's no such thing as division of matrices. What we have is the inverse, or various aspects of inverse. We're actually going to talk today about the inverse matrix and the pseudo-inverse matrices. And it's those matrices that define division for matrices. Okay, for a square matrix A, so notice something about the matrix. First of all, it needs to be square. The inverse, if it exists, is a matrix that satisfies these two properties. That is, when I multiply A times the matrix we call the inverse, we get the identity. If we multiply it from the other direction, we also get the identity. So the inverse is a matrix that is defined by these two properties. Okay? Later on, we're going to come back and define something called a pseudo-inverse that is also defined based on properties. So this is important. So notice it's not defined. So it's often, when you come to a class in linear algebra, it's often defined in terms of how you calculate it. That's actually not the appropriate way of defining it. So here's one way to calculate the inverse. The inverse matrix, if it exists if and only if the determinant of A is non-zero, in which case the inverse is given by the adjugate divided by the determinant. So notice, obviously, we need the determinant to be non-zero or we can't divide by it. And then there's this thing called the adjugate. Sometimes you'll see it referred to as the adjoint, but that's actually not exactly correct. So we're going to use the correct term adjugate, which is, it has the same three initial letters, ADJ. So this is the inverse. And we're not going to specifically show how to compute the inverse, although actually we will show how to compute it, but we're going to do it kind of in a roundabout way. We're not going to actually use this formula to compute the inverse. Okay, we're not going to use this formula primarily because of the way the adjugate is defined and also the determinant. But we will talk about the determinant more than we will about the adjugate. So here are some properties of the inverse. Again, assuming the inverses exist. If I take the inverse of the inverse matrix, I get the original matrix back. And again, you can go through and prove these properties just by the definition of the inverse. So for example, the matrix, if I take this matrix A and multiply it by A inverse, I'll get the identity, and vice versa. So you can easily go through and show these properties using the basic properties of the inverse. So if I take a constant times the matrix and I take the inverse, I get 1 over the constant times the inverse. If I have the determinant of the inverse matrix, that's 1 over the determinant of the matrix. Okay, so we have that relationship between the inverse and the determinant. If I take the transpose of the matrix and then I take the inverse of that, that's equal to the transpose of the inverse matrix. You can go through and show this, and that we can just write it this way, a to the minus t, where t is the transpose. So this is actually an abusive notation, but it simplifies having to write all these parentheses and stuff. if I have a matrix product where both of these matrices A and B are invertible, and when I take the inverse of that product, I get the product of the inverses in the opposite order. So this is a similar property to the transpose, again, when both are square and invertible. So lots of properties of the inverse. Now for partition matrices, if the matrix A, the submatrix A, is non-singular, that is, it has non-zero determinant, then we can factor this matrix into a product of three matrices. And so notice this involves the inverse matrix of A. So it's a product of three matrices where, again, we're assuming that the various submatrices have these various dimensions. And so why would we want to factor the matrix this way? Well, that's a good question. Notice that each of these matrices is block triangular. So this is lower block triangular, this is upper block triangular, and this is actually block diagonal. Also, along the diagonal for these two matrices, we have just identity matrices, and that actually makes things very simple if you want to do certain calculations with them. So if this submatrix is non-singular, we can factor that partition matrix this way. If this submatrix down here is non-singular, then we can factor it this way. So we have these various factorizations. So if, again, the determinant of A is non-zero and we have this factor, we can compute the inverse of this matrix this way. Okay, so it turns out that these matrices all have fairly simple inverses that we can compute. So whereas this matrix itself may be very complicated to compute, we can compute these individual inverses, multiply it all together, and we get the overall inverse. So these matrices actually have simple inverses. What do the inverses look like? This is what they look like. So if I have identities along the diagonal and then something off the diagonal, the inverse of that matrix is just this. So again, that's simple to calculate. If I have a block diagonal matrix and I compute the inverse of that, that's the inverse of the diagonal blocks. Okay, again, fairly simple to calculate. It's not a huge calculation. I do have these smaller inverses to calculate. So in a sense, and here's the lower triangular. Here's the lower triangular inverse. So in a sense, the inverse of a square matrix like this boils down to something that comes out to be these simple inverses, this one, and then smaller inverses. Okay, so instead of having the full n plus m dimension matrix, I now have an n by n inverse and an m by m inverse. So I can break it up into smaller inverses, and so we have that property. Here are some more properties of inverse. If I have a matrix like this, the sum inverse, I can go through and show that it has, as long as the inverses exist, it can be written out this way. So this is like an expanded form of the inverse. Similarly, if I have matrices multiplying on left and right of an inverse of a sum, I can bring those inverses inside the overall inverse. And similarly, if I take a similarity transformation, that is, if I take the inverse of a matrix and the matrix, I take them inside the inverse, I get that happening. So if the determinant is not zero, we have these properties. If AB is equal to AC, this is true so as long as the determinant is not zero, then these two products are equal if and only if B is equal to C. So that's A multiplied on the left. If A multiplied on the right, again, we have the same kind of thing if B is equal to C. Now, if the determinant is not zero, then the linear system of equations has a unique solution. X is equal to A inverse B. Okay, so in this case, if the inverse exists, then we have this nice solution. It's the inverse. We take the inverse times B, and we're good. So this is the situation for a unique solution. Okay, so now what happens if we can't take the inverse of a matrix? So it turns out that we said if the matrix is square and if the determinant is not 0, then we can compute the inverse of a matrix. Okay, the matrix is said to be non-singular in that case. So what happens if our matrix is not square? Haha! Woohoo! That's a big difference. Then we can't solve the problem. We can't solve the problem using an inverse. What about if the matrix is square, but it is singular? That is, it has 0 determinant. What can we do? Are we hosed? Are we just completely, is there no possibility of finding a solution? So that brings us to something called the pseudo-inverse. The word pseudo meaning something like false, but it's not really false. It's not really a true inverse, but it has some properties like an inverse, and in particular, it can be used in solving the linear algebra equation. So the pseudo-inverse is the main tool that we're going to be using in solving the linear algebra equation, and we're going to see it for a number of different kinds of problems. We're going to be using it for different kinds of problems, and for one problem, it solves one aspect of the problem. For another problem, it solves another aspect of the problem, and we're going to use both aspects of it as we go through. So we're going to use one aspect, for example, when we do system identification. We're going to use another aspect when we do the control design. So the solution to this linear algebra problem is very important, and it has its roots here in this concept of a pseudo-inverse. So let's see what this has to say. Okay, for a matrix n by m, so notice we're not assuming a square matrix. It could be a square matrix if n is equal to m. Okay, but the pseudo-inverse A, and here we use the superscript plus to indicate the pseudo-inverse. The pseudo-inverse exists and satisfies the 4 properties. So now notice here, this could apply to a singular n by n matrix. Okay, so whereas the inverse only exists if the matrix is square and non-singular, the pseudo-inverse always exists. Always exists. Ah, yes. Okay. So remember, the inverse was defined by 2 properties, right? Here, the pseudo-inverse is defined by 4 properties. Okay. So all of these must be satisfied for the pseudo-inverse. It turns out that if any matrix satisfies these 4 properties, then it is the pseudo-inverse, and there's only one pseudo-inverse. So here's the first one. A times A pseudo-inverse A is equal to A. And then we have the opposite equation. A pseudo-inverse A pseudo-inverse is equal to A pseudo-inverse. So remember, in the definition of the inverse, notice the definition of the inverse was based upon multiplication, right? We take A times that matrix if we get the identity, and if we multiply in the opposite direction, we get the identity, then that matrix is the inverse, okay? So the inverse is defined in terms of multiplication, not division. Similarly, the pseudo-inverse is defined in terms of multiplication, not division. And so we have these properties. So notice that if we use the matrix, so if the matrix is square and the inverse exists, notice that you can go through and show that all of these properties hold, okay? So if the inverse exists, it is the pseudo-inverse and vice versa. The pseudo-inverse is the inverse if the inverse exists. So where the pseudo-inverse is powerful is when the inverse does not exist. Okay, so we have these 4 properties. So this basically says that if I take the product A times A pseudo-inverse, that product is symmetric, right? It's equal to its own transpose. Similarly, if you multiply them in the opposite direction, we get these are equal to their own transpose. So remember that if we take the inverse matrix times the original matrix, we get the identity, and that's a symmetric matrix. And I can multiply it in the other direction, and it is also a symmetric matrix. So these 4 properties actually are easily satisfied by the inverse if the inverse exists. Okay, so what happens if the inverse doesn't exist, or you know, how else can we compute it if we don't have a square matrix? Well, here are, I'm going to show you some formulas for computing the inverse in various situations. So if the determinant is non-zero, then the pseudo-inverse is in fact the inverse. So we basically went through and showed that already. Now, if the determinant of this product, A transpose A, notice that A transpose A, you can always, for any matrix, non-square matrix, I can always multiply it by its transpose on either direction. Now, these two matrices may be a different size, but I can always multiply them, and the resulting product will always be square. So if this product is not zero, then I can compute has non-zero determinant. Then I can compute the pseudo-inverse this way. So notice that non-zero determinant is required to get this product inverse. Okay, but I have a formula for that. If the determinant of this product is not zero, then the pseudo-inverse is given by this formula. So in this case, this would be the case when the matrix A is tall and thin. Okay, this case here. This case here is when the matrix is short and fat. Okay, and so that's the kind of situation. In other words, that's the only time if the matrix is short and fat, this will automatically not be this will have zero determinant. This product, the way it's multiplied out. Similarly, if it's tall and thin, this product will automatically have zero determinant. So this can only be used if the matrix is tall and thin. This can only be used if the matrix is short and fat. Okay. Now suppose the matrix A can be written as a product of two matrices where the determinant of F transpose F is non-zero and the determinant of GG transpose is non-zero. Notice we're using, so this one's going to be tall and thin, this one's going to be short and fat. Okay. Then the pseudo-inverse of A can be written as the pseudo-inverse of G times the pseudo-inverse of F, and the pseudo-inverse of F can be given by this, pseudo-inverse of G is given by that. So we're actually using both of these formulas here, and so we can actually compute the pseudo-inverse of a matrix if we can factor it this way into the product of two matrices. So it turns out that the only time these three methods of computing can be used is if the matrix is full rank. Okay, so this would be the case if it in full rank means all the columns are independent, all the rows are independent. Okay, in this case, this implies that all the columns are independent. The rows may be dependent, but the columns are independent. This one basically says that all the rows are independent. Okay, the columns may be dependent on this, but the rows will be independent. Okay, and this one basically says I can take a matrix and have a part of it that has independent columns and a part that has independent rows. Okay, so let's look at an example of computing using some of these properties. Okay, so here's this matrix. I want to compute the pseudo-inverse of this matrix. Well, I can go through and show that A transpose A, if I take this transpose, that gives me a row times a column. That's going to give me the scalar value 1, which is invertible. Okay, and so this quantity inverse, 1 inverse is just 1, times A transpose, I just get the transpose. Okay, so this one is fairly straightforward to compute, and I can go through and show that A pseudo-inverse times A itself is equal to 1. That's clearly symmetric. If we multiply it, so that's A times A pseudo-inverse, so I multiply in the opposite order now, I get this matrix, which is square, but it's singular, and but it's still symmetric. Okay, the off-diagonal elements are the same. Okay, so we see that for this simple case. All right. So here, this is our example. We're going to look at all four properties. So we see that these two properties are satisfied. What about the other properties? So here we take A times A pseudo-inverse A, but we notice that A pseudo-inverse A is just 1, and so we get A back. We do it the other way, A pseudo-inverse A pseudo-inverse. We recall that A pseudo-inverse A is just 1, and therefore we just get A pseudo-inverse. So these properties. So for the given matrix, the matrix that satisfies the four properties is given by this. Okay, so that is the pseudo-inverse. Now those are the four defining properties for a pseudo-inverse, but that does not mean that that does not mean that those four properties make it easy, can be used to easily compute the pseudo-inverse. Okay, does not mean that. So here's a square matrix. So notice that the third column is the sum of these first two columns. So this matrix is singular. It's square and singular. Okay, since it's square, determinant 0, we can't use any of the first three formulae, because the first three formulae requires either all the rows are independent or all the columns are independent. Okay, in which case we can compute it. But in this case, we don't have independent rows or columns. Okay, so we have that. All right. However, since the matrix A is however, we can always use the fourth property, which requires we find an F and a G. So how do we find an F and a G so that A is equal to F times G that allows us to compute the pseudo-inverse? Incidentally, if we have a matrix in MATLAB, we can use the command pinv to compute the pseudo-inverse of the matrix. So what I'm talking about here is primarily the situation if you don't have access to MATLAB and you're trying to do calculations. Okay, so we have this matrix. We notice that the first two columns are independent, the last one is dependent, so we ignore that last column and just choose the first two columns. Okay, so we form the matrix F from that, and we go through and show that the determinant of F transpose F, so when we multiply this matrix times the transpose of this matrix times itself, we get this matrix. The determinant of that is 3, which is non-zero, so we're good. So anytime you have a set of a matrix with independent columns, this matrix will always be non-singular. Okay, so that there's a direct relationship between those columns being independent, linearly independent, and this matrix product being non-singular. Okay, so we found an F, and the way to choose the F is that you just choose the independent columns of the matrix, all the independent columns. Okay, so we now compute the pseudo-inverse of F, and so here's the pseudo-inverse formula. So we take this inverse times F transpose. When we multiply it all out, we get this. Okay, so it's not that pretty, but that's what we get. So that's F pseudo-inverse. Now to compute G, it turns out that we can compute G this way as F pseudo-inverse times A. So here's F pseudo-inverse, here's A, multiplying it out, I get this matrix, which actually surprisingly comes out rather nice looking. But anyway, that's what we get. So we have this matrix as G, and so we can go through and show that if we multiply F times G, we get the original A matrix back. So we have actually done the factorization. So that's how we would get our F and G. So now we would compute the pseudo-inverse of A by computing the pseudo-inverse of G times the pseudo-inverse of F. So here's the pseudo-inverse of G. I've gone ahead and calculated it. Here's the pseudo-inverse of F. We've already seen that before. Multiply the two together, we get this matrix. So this is the pseudo-inverse of A. And notice that it doesn't, so for example, this has lots of ones and zeros. This doesn't look like that at all. Okay, so it's very different, but it does. You can actually go through and show that this matrix satisfies all four properties of the pseudo-inverse. So it's a lot of work, definitely more work than, in fact, we have to actually compute two pseudo-inverses to compute the one pseudo-inverse. So it's more complicated, but at least we have a procedure for doing it. Okay, so we have a procedure. So now when we come to our basic linear algebra problem, AX is equal to B, there are three possibilities for the solution of this equation. We have the overdetermined problem. So in a sense, the basic linear algebra problem boils down to three linear algebra problems. Okay, so that's part of what makes this deceptively simple. I mean, is it deceptively simple or deceptively complex? I think it's deceptively complex. It looks simple. It's complex. So the overdetermined problem basically you have more equations than you have unknowns, and the equations may be inconsistent. That is, you may have equations that disagree with one another. As a result, there is no exact solution to that set of problems, to that set of equations. And you say, well, if my equations are not consistent, there's no exact solution, what's the point? Right? What's the point? Why even work with a problem like that? Well, it turns out there are a lot of useful problems. In fact, our system identification problem is going to be a problem like that. So, next we have the exactly determined problem. Whoa. Okay. So here we have, again, no exact solution. Now, the second case is the case when we have an exactly determined problem. That is, you have as many equations as unknowns, and all the equations are consistent. Okay, we'll talk a little bit about what consistency is here in just a minute. And in this case, we get a unique exact solution. So there is an exact solution, and there's only one exact solution. Okay, so that's the exactly determined problem. And then finally, we have the underdetermined problem. That is, we have fewer meaningful equations than unknowns, and the equations are consistent. In which case, we can get an infinite number of solutions. And by solution, I mean exact solutions. Infinite number of exact solutions. So those are the three possible problems. And in the overdetermined case, it is solved using what's called the LeastSquares solution, which involves the use of the pseudoinverse. For the exactly determined case, the solution, the exact solution, follows using the inverse. And finally, for the underdetermined case, all solutions are given by a formula that looks like this, where we'll talk about something called the orthogonal complement, and then R is any compatible vector. So here, this is the case when we get infinite number of solutions. Since R can be anything, then we can write the general solution this way. So we'll come back and see how all of these are defined a little bit later in turn. Okay. By way of example, here's an A matrix, here's a B matrix. Each of these rows corresponds to a line, right? A is multiplied by X, so X is two-dimensional. Okay. And so in two-dimensional space, each of these rows corresponds to a line. So minus 1 times x1, 1 times x2, plus 1 times x2 is equal to 2. So that's a line. And so this set of matrices defines a set of 3 lines. So this is the case when we have more equations than we have unknowns. Okay? And in this case, we notice, so here are the 3 lines that we get, and notice that there are no intersections between these lines. So in this case, there is no solution, no exact solution. Okay. Here's a case when, again, I have three equations and 2 unknowns, and those correspond to these lines. Okay. So again, each of these rows corresponds to a line. Notice that in each of these examples, these guys here are all 1s, which basically means that x2 is equal to something times x1 plus something. So we have like slope and intercept kind of formula. You can rewrite it that way. And so in this case, notice I have 3 lines, and the points of intersection are points where I have 2 equations that agree with one another, that are consistent with one another. So notice that in each of these cases, these 2 equations are consistent with each other. These 2 equations are consistent with each other here, and these 2 equations are consistent. But notice there's no place where all 3 are consistent in the same time. So there's no unique solution. There's no common solution or no unique solution. So this is a case when you have the 3 lines, and the 3 lines give us a unique solution. There's one point where all 3 equations agree. Okay, and so that's the set of unique solutions. Okay, so in this example, again, each row corresponds to an equation, and we can actually write the equation this way. So I have a row that looks like this. So the 1 here, this quantity is minus m. Okay, and then I have the b, which is the coefficient here. So notice this b is not, this is a vector b, this is the scalar b. But I can rewrite it this way. I can multiply this out, solve for x2, and I get this equation. Actually, that should be x1. And so I get a line. So each of these rows corresponds to a line. And so here, by plotting these lines, we can see how they intersect or not. Similarly, here's another set where these two guys are parallel to one another, and then this guy intersects. Okay, so again, no common solution. Here's an example where I get a unique solution. I have this line, and then there are two lines here that overlap one another, and so you get again a unique solution. And here's the case when all three lines are piled on top of one another, and so in which case we get an infinite number of solutions. All three lines are what are called collinear. They're lying on top of one another, and so we get an infinite number of solutions. So this is an example of how we can get no solutions, one solution, or infinite number of solutions. So next we move on to the least squares problem. And you're saying, well, that's kind of an interesting picture. What does that even mean? Well, we'll actually use this picture to help us define something, and something called the projection theorem. So in order to back up and understand the problem, and again, the problem is deceptively complex. It doesn't appear as complex as it really can get. So we're going to get a little deep here into some linear algebra theory. Okay, some little bit of depth. So the first thing we're going to talk about is something called the inner product. So if I have a vector, which is like a row, a column. If I have a column, I can go through and show something called the inner product. Okay, and for our problem, the inner product can be shown to be defined this way: x transpose y. Okay, the inner product, which is basically the row times the column, so that we can define that as an inner product. And you can go through and show that the inner product is a function of two vectors that satisfies these properties. Okay, so that is, if I take the inner product of x and y, that's equal to the inner product of y and x conjugate if x and y are complex. For the most part, we're going to be using real vectors, and so that we don't need to do the conjugate. But if you end up using complex things, then we need to have that. In which case, instead of using the transpose here, we would use the complex conjugate transpose, and then that would work. The inner product satisfies this if I have x times alpha y, some scalar times a vector. I can actually pull that scalar out and then multiply by the inner product. Okay. If I have a sum of two vectors, inner product with another vector, I can break up this inner product into the sum of two inner products. Okay, this way. If I take any element and I take the inner product of that vector with itself, I should get something non-negative for any element, for any vector, n-dimensional vector. If I take the inner product of some vector x with itself and I get 0, that can happen if and only if the vector x itself is 0. Okay, so I can't get 0 otherwise. All right, so that's the definition of the inner product. We can use that definition to establish something called the norm. So the norm is a function of just a single vector, and it satisfies these four properties. So notice x, the norm of x, so x is like the size. The norm of x is greater than or equal to 0 for all x, so the size cannot be negative. The size is equal to 0 if and only if the vector itself is 0. So the size is 0 if and only if there's 0 size, the vector itself is 0. If I multiply by a scalar, the scalar comes out. Okay, and the magnitude of the scalar comes out. And if I have the norm of a sum, that's less than or equal to the sum of the norms. Okay, so again, we can think of the norm as the measure of size, and for vectors, this is a definition for that we can use for the norm. It's the square root of the inner product of x with itself. So we know the inner product of x with itself satisfies these two properties, and so, but the inner product of x with itself does not satisfy this property. But once we take the square root, then it does satisfy this property. So we can go through and show also this property, which is called the triangle inequality. So this is like a generalization of Pythagorean theorem with respect to n-dimensional vectors and sizes. So, okay. So those are some important quantities we're going to be looking at, important functions of vectors. So as we look at the solution of the linear algebra problem, it's important for us to have the right tools to use in order to evaluate the problem and its solutions. So here's the least squares problem. Given a vector B and a matrix A, okay, we want to minimize the error, okay, where the error as a function of x, where x is some vector in Rn, and the error is given by b minus ax. Okay, so notice that if b is equal to ax, then this error is 0, and that's as small as you can get. But we're looking at here at the problem when the error is not 0, when there is no x that makes this 0, and so we're looking at the smallest value. So it turns out there are actually two cases we can look at, the overdetermined case and the underdetermined case. Now, you can consider the exactly determined case as actually included in here or included in here. So we talked about 3 different cases. The middle case can be lumped into either of these two accurately. So this is the problem. We're basically trying to find an x. So this is the minimum. We're minimizing over all x in n-dimensional space of this error. Okay, the norm of that error squared. So notice by taking it squared, remember when we talked about the norm being the inner product of x with itself, square root. Here, by taking the square, we can drop the square root sign, and that just makes things a little simpler. So the question is, why is it called least squares? So if you think of this as a column vector, when I multiply a times x, I get a column vector. If we subtract these two, I get a vector. Okay, so and each of the elements in this vector is a function of x. That is, it's a function of all the elements of x. Okay, so that's what we have. And so desiring to minimize this quantity, the norm squared of the error, that's the inner product of the error with itself. So notice here, error is a function of x. This inner product is equal to the error transpose times itself. And so since the error is these elements, we get these elements transpose times itself. When we multiply it out, we get the sum of the squares of the elements of the error. So the sum of the squares, and so the least squares is the smallest sum of the squares of the elements of the error. Okay, so that's why it's called least squares. So we're trying to minimize or get the least sum of the squares of the elements. That's why it's called least squares. Okay, now we're going to move on to a little bit of what I call subspace theory. So this is, we're going to actually be looking, again, we've been talking about vectors in n-dimensional space. Well, it turns out that in n-dimensional space, if you think about 3 dimensions, you can talk about a subspace as being a part of the overall space. So when we talk about subspace theory, there are a couple of different things we're going to be looking at in terms of subspace theory that are important for us. In particular, there are 2 important spaces that we're going to be looking at. The first is what's called the null space, or the kernel. That's the set of vectors that multiply a matrix and give 0, result in 0. So it turns out that for some matrices, there are non-zero vectors that you can multiply that matrix by and get 0. So even though neither of the 2 elements are 0, well, you can multiply them and get 0. So that's kind of weird, different. It's not the same as numbers. So the second space is the set of all possible outputs when you multiply a matrix by a vector. Okay, so those are the 2 important spaces. So let's look at these. So if we think in terms of functions, if you think of, so a function of x. In this case, our function is ax. But if you just think in terms of a function of x, you have an input space. Okay, that's often referred to as the domain of the function. And then you have an output space. That's the space that the output of the function lives in. So remember that, for example, for a case like this, if we have an m by n matrix A, m by n, that means the input space is n-dimensional, the output space is m-dimensional, and so these two spaces are not the same. Okay, so we need to think in terms of the fact that we can have different spaces. So the null space is actually in the input space. And so every element, any element in here, when I plug it in the function, I get 0. Okay, so this may be a non-zero space, but it is non-trivial. So notice that if we plug in the value 0, we will always get 0. So the null space always has the 0 element in it. Okay, so that's the null space. Now the range is if I take every element in the input space, I put it through the function, I in general will get some space over here. Okay, and this space may not fill the entire output space. So for example, again, if A is m by n, if n is less than m, then this will only fill an n-dimensional space, which is less than m-dimensional space. Okay, it turns out you cannot fill more space than you started off with. Okay, so the kernel or the null space. So if any element is in the kernel, so if any element is in this space, then we have this relationship, ax is equal to 0. So if x is in the kernel of A, ax is equal to 0. Okay, so the kernel is non-trivial if there is a non-zero x such that ax is equal to 0. So notice if I plug in 0 here, I'll get 0. So 0 is always in the kernel of A. So if there is something that's not 0 in the kernel of A, then we say that kernel is non-trivial. Again, 0 is always in the kernel of A. So how would we define the kernel of a matrix? Well, we start by multiplying by a generic vector, set the result equal to 0, and see what you get. So here's this matrix. We'll start off with this. Okay, we're going to take that and multiply by a generic vector, v1, v2. I don't know what, these are just symbols. Okay, multiply this out, and I get this. Okay, so I have a 0 there, and that's equal to 0. So, I'm going to set that equal to 0 in order to see what the null space looks like. So what this says is that if I set this equal to 0, then v1 must be equal to 2 times v3. And what about v2? What does this equation have to say about v2? It doesn't say anything. So as a result, v2 could be anything. Okay, so it turns out that you have an infinite number of vectors in the null space. Okay, an infinite number of vectors. And it turns out that if you have any non-zero vector in the null space, then you actually have an infinite number of vectors in the null space. You can actually go through and show that. Okay, so for this particular problem, there are 2 linearly independent possibilities. For example, I could choose v2 to be 0, and okay, so v2 could be 0 here, and then I choose, for example, v3 to be 1, and as a result, v1 is going to be 2. Okay, so that's this vector. Or I can choose v1 to be, I can choose v3 to be 0 and v1 to be 1. I'm sorry, v2 to be 1, in which case I get this. So these two are clearly linearly independent. And so as a result, this set of vectors spans the null space or the kernel of that matrix A. Okay, so it spans that, it fills up, any element in the null space of A can be written as a linear combination of these 2 vectors. That's basically what it means to span the null space. Any vector in the null space can be written as a linear combination of those 2 vectors. So in terms of linear algebra theory, they form a basis of that space. We can also define the matrix called the orthogonal complement of A. So the matrix, a matrix written like this, is the orthogonal complement of A, or sometimes called A perpendicular, A perp, if that product is equal to 0. Okay, so the orthogonal complement of A is made up of a basis of the kernel. And so in our case, this column and this column are independent. They form a basis. The matrix formed from that, or a matrix formed from that, is the orthogonal complement. So there's more than one orthogonal complement, because I can take this matrix and multiply by any constant, and that product will, if I multiply it out, I'll still get 0. Okay, so that's the null space. That's actually fairly simple to compute, fairly simple to work with. The one that's a little bit more complicated to think about and work with is the range, or sometimes the range space. So an exact solution to the linear algebra problem exists if and only if B is in the range of A. Okay, so that is, if I map the entire space through my function, I get into the range. If the B that I'm looking at is not in this space, then I don't have a solution, because basically this is the space of all possible combinations of vectors that I can get from my function. So if the B that I get is outside of that space, then there is no exact solution. Okay, so in other words, the vector B is in the range of A if and only if there's, so if B is in here, that means there was some X that got me there. Okay, so that's the idea of the range. Okay, that's the idea of the range. If B is not in the range of A, then no exact solution exists for the linear algebra problem. This basically means that the equations are not consistent. And here's a way we can test for consistency. B must be equal to A pseudo-inverse, A times A pseudo-inverse times B. Or alternately, I minus A pseudo-inverse must have B in its null space. Okay. If these are satisfied, then the equations are consistent. Otherwise, if this is not 0, then the equations are not consistent. So this is a test for consistency. All right, so we have the range and the null space. Those are our main spaces. We're now going to move on to talk about the general solution of the linear algebra problem. Given the linear algebra problem, AX is equal to B, where B is in the range of A. Okay, so that is, there is a solution. Okay, so this is when we say general solution, this is the general exact solution. Okay, so all exact solutions to the linear algebra problem are given in this form: A pseudo-inverse times B plus the orthogonal complement of A times some matrix R, where R is any vector of commutable dimensions. Okay, so now how do we know this is an exact solution? Okay, how do we know? Okay, so to verify that this is a solution, we know that since the equations are consistent, then B must be equal to A pseudo-inverse times B. Okay, so that's required for the equations to be consistent. If the equations are not consistent, then no exact solution exists. Okay, so we must have that. So A is equal to, so plugging in the X. So we're going to first see if this X actually does solve the problem. So let's plug it in. A times X, so here's X. Okay, we're going to distribute A through this equation. So A pseudo-inverse B, A perp R. A pseudo-inverse B, we're told, is equal to B. So this quantity is B. A times A perp is 0 regardless of what R is. And so B plus 0 is just B. So we see that this is a true solution regardless of R. And the reason it's regardless of R is because A times A pseudo-inverse is 0 regardless of R. Okay, so this is the general solution. So in the case when we have a solution, it's possible that we may have an infinite number of solutions. So this is in this case, when we have an exact solution, it's possible to have an infinite number of solutions, and all the solutions can be written in this form. Okay, so that's important to us. Okay, well, let's get back to the least squares problem. Again, given A and B, we want to minimize the norm of these errors. Again, we have these two cases, the overdetermined case in which we're assuming the equations are inconsistent, the underdetermined case where we may have exact solutions, and in particular we may have an infinite number of exact solutions. So those are the two situations we're going to be looking at. So in the overdetermined problem, B is not in the range of A, and so no exact solution exists, and so we're seeking the best approximate solution. That is, we're trying to find the x that makes this norm quantity as small as possible. So we've already kind of stated the answer to this problem. That is that x is equal to a pseudo-inverse times b. So the question is why? Why is that the solution? Well, this picture kind of illustrates what's going on with that. So if we think of this plane down here as the range of A, and here's our vector B, okay, so notice that B is not on this plane, which means it's not in the range of A. Okay, so we have that. So we do not have an exact solution. And so we're going to try to find the vector in this plane that is as close as possible to the vector B. Okay, and so you can go through and show that the one that is the closest is the one that's a projection of this vector onto this plane. So here this shows the projection as kind of like a shadow of this vector. So this is like a problem where our matrix gives us an output that's a two-dimensional vector, but our B is in 3 dimensions. Okay, and so what we want to do, what we want to show is something called the orthogonality principle that says that the error, that is the distance between this vector and the actual vector B, that there's orthogonality here. There's a orthogonality is like perpendicular. So orthogonal is a general case of perpendicular. So for example, if I have a vector, an orthogonal vector would be a vector like this, right? That would be perpendicular. But you can also have an orthogonal vector that's orthogonal this way. Actually, there's an infinite number of orthogonal vectors to the other vector. So, but it's a generalization of the concept of perpendicular. So we know that if we can define things in terms of perpendicular components, that simplifies a lot of calculations. Okay, so this is what we're actually going to show as we go through here. So how do we talk about that? Well, we've already defined the inner product of x and y, and we saw that this inner product is related to the norm this way. And we can define orthogonal, that is, 2 vectors are orthogonal if their inner product is 0. Okay, their inner product is 0. Then the 2 vectors are orthogonal to one another. Okay, so it's not hard to show this. Okay, it's not hard to show this. We can, for example, use a 3-dimensional vector. Okay, so we know that in terms of the axes x, y, and z, that x would be, for example, a unit vector in the x direction would be 1, 0, 0, right? If you have a unit vector in the y direction, that would be 0, 1, 0. So if I take the x vector 1, 0, 0 transpose times the y vector 0, 1, 0 and multiply them together, I'm going to get 0. Okay, so again, that's just kind of an example of the orthogonal. That's a very simple example of the orthogonality. Okay, so orthogonality, orthogonal. Say it with me, orthogonal. Okay, that is the concept of being perpendicular. Now it turns out this inner product, actually, there's a relationship between the 2 vectors. If I take the inner product of x and y, I can go through and show that's equal to the norm of x times the norm of y times the cosine of the angle between the 2 vectors. Okay, the cosine of the angle between the 2 vectors. And so we know that if the angle is 90 degrees, we're going to get 0, orthogonal. So this is really kind of a concrete way of thinking about perpendicular. Now notice the vectors x and y can be in n-dimensional space, not even 3-dimensional, but n-dimensional space. And we can still define the concept of this angle that way. Okay, so this is actually a really powerful concept to think of that way. And so when the angle is 90 degrees, we're going to have orthogonal. the two vectors be orthogonal. Okay, so we come to this thing called the orthogonality principle. And in this process, we're going to define x star. That's our star player. That's the best x for our problem. And now we're looking at the equation ax is equal to y as opposed to ax is equal to b, although you could use b or y, whatever. So a pseudo-inverse times y. That's our star players. So that's what we're expecting to be the minimizer, the minimizer, the optimal solution to our minimization problem. So for any x, we're going to define the vector, the error, which is a times x minus y. So there's our error. We've seen that before. So now for the star, we're going to define the error star. That is when x is equal to x star. And since x star is equal to a pseudo-inverse y, we have this expression. Error ax star minus y is equal to a pseudo-inverse times y minus y. And now I'm going to define the difference between the error and error star. Okay, so this bold uppercase error is the difference between these two little errors. Okay, so got a lot of errors. Runs, drips, and errors. Got a lot of errors going on here. So now, here's the orthogonality. Okay, I have this error times this error. So this error, this little error, notice here, this should actually be the error star. That shouldn't be just the error. That should be the error star. So if I look at this equation here, I can factor out y, and so I get the error star. So when I factor out y, I get this. So this should be actually the error star. Oh, there we go. Okay, so the error star now is equal to a pseudo-inverse I minus I transpose. Okay, so why is that? Okay, again, if we factor out this, factor out y, we get a pseudo-inverse minus I times y. Okay, that makes sense. Now, if you recall, a times a pseudo-inverse must be symmetric. The identity is symmetric. The difference between the two will be symmetric. And so that's why we can get the transpose here. Okay. Now, why do we need the transpose? Because when we take the inner product, we take this quantity transposed times this quantity. So when we take this quantity transposed, so there's the transpose times that quantity. This quantity transpose becomes y transpose, all of this stuff transpose, but transpose just gives me the matrix. I can now distribute A into this matrix, and I get a pseudo-inverse A minus A, and by definition of the pseudo-inverse, that must be 0. Okay, so we can see the orthogonality. Okay, we can see the orthogonality there. So that's important. So this error is orthogonal to this error. So now if we look at the overall cost, a times x minus y, the norm of that squared, that's the error. This quantity is the error. Inner product with itself. Okay, so I'm going to take this quantity, I'm going to add and subtract the error star. Okay, in both places. So this quantity here is what we call the big E. Okay, so the big E plus the error star, big E plus the error star, and then I switch the places. All right. So I have this inner product with itself. Now I can, by the basic properties of the inner product, I can divide up this inner product of two sums into 4 inner products. That's like the inner product version of FOIL, right? Firsts, inners, outers, lasts. Okay, so that's the vector version of FOIL. And so inner product of the error star with itself, inner product of error star with the big E, inner product of the big E with the error star, and inner product of the big E with itself. Okay, we've already shown that this quantity is 0. We showed that in the last slide. And this is just the inner product in the opposite order. And so these two must both be 0. And so we have this quantity here. So if you look at what this is error star norm squared plus this big E is the error minus the error star. And so this is the norm squared. So notice that this quantity, each of these quantities is non-negative by the definition of the norm. And so in particular, this guy is non-negative. And so all of this is greater than or equal to the norm of the error star. We get equality if and only if this quantity here is 0. Okay, if and only if. Okay, and so that means that the error must be equal to error star. In order for this to be 0, the error must be equal to error star. So that means that's where you get the smallest norm. So that when we minimize that quantity with respect to x, we're choosing the x so that x is equal to x star. Okay, so a minus x in norm squared is given by this. This is minimal when x is equal to x star. So x is the minimizer. For any other x, this quantity is greater than this quantity. And so the x that's equal to x star is the minimizer. So that's the x we're looking for in terms of the least square solution to the overdetermined problem. So let's kind of back up a little bit here for this overdetermined problem. In this case, we have that the vector y is not in the range of A, so no exact solution exists. So we seek the best approximate solution to this problem. We've stated that the best solution is given by the pseudo-inverse of A times y. And so for any other x, we get a larger norm for our thing that we're trying to minimize. So this is, in fact, the minimizer. Okay, so how do we go about solving the underdetermined problem? So we've talked about the solution to the overdetermined problem. How do we solve the underdetermined problem? Well, we have already seen that the general solution to the underdetermined problem is given by this formula. X is equal to A pseudo-inverse times y plus A perp times r, where r can be anything. And so since x can be anything, this basically describes or parameterizes an infinite number of solutions. That is, r is the parameter. As for a different r, I'll give it a different solution. And every solution that satisfies this solves that linear algebra problem, ax is equal to y. Okay, so regardless of what r is, it's a solution. So what we're going to come back later is we're going to define something called a quadratic program. And the quadratic program is now going to take all of these solutions and it's going to look for an r that minimizes something else. Okay, and so we'll talk about that quadratic program just in time. That is, when we need to use it, we'll pull that tool out. Okay, but for now, we have the underdetermined problem is given by the solution of this, by this general solution to our equation. So, this is the linear algebra problem. It's a little bit long, but thanks for sticking with me. Thanks for watching.